Good evening, everyone. So we are today going to start our new topic on the amorphous systems. In the last class, we had discussed about the last topic that was related to co-crystals. With that, we have finished our discussion on the crystalline part of the solid state. We are now going to move over to another important aspect, that is the amorphous pharmaceutical systems. This is the classification system which we had discussed earlier also, wherein we had discussed that a chemical compound can have an external habit and then it can have an internal structure. The internal structure could be either crystalline or it could be amorphous. We have already discussed about the crystalline internal structure. We are today going to begin our discussion on the amorphous phase. An amorphous phase, or what we also call as a glass, can be defined with reference to a crystalline solid. Similar to a crystalline solid, an amorphous solid may have short-range molecular order, but unlike a crystalline solid, an amorphous solid has no long-range order of molecular packing or well-defined molecular conformation. This becomes the most important aspect, that the amorphous solids can only have a short range order and they do not have a long range order. A long range order, if you remember, is characteristic of the crystalline form, and that is what is responsible for the intermolecular arrangement of the molecules in a repetitive three-dimensional order. So the amorphous solids lack long range and long range three-dimensional molecular order. They will only exhibit a short range order over a few molecular dimension. This is the unit cell of celecoxib, which we had seen earlier also, wherein the molecules of celecoxib are arranged in a very ordered fashion in the three-dimensional space. So this is the three-dimensional ordered molecular arrangement of crystalline celecoxib. In comparison to this, this is the amorphous celecoxib. Remember, this particular diagram has been generated using computer software, because you cannot find the structure of the amorphous form by using a tool like single crystal XRD, because there is no definite diffraction pattern from the amorphous form. So you cannot determine the arrangement of the molecules in the amorphous form. So this is the cluster of molecules of amorphous celecoxib. So here also we have similar molecules of celecoxib, but as you can see, they are arranged in a disordered manner. You can see some of the molecules may be in ordered state with respect to their neighboring molecule, but a long range order is missing in the case of amorphous celecoxib. And this would be true for all other amorphous systems as well. Most of the APIs that exist in the crystalline form can also be converted to their amorphous form, and the generation of the amorphous form would mean that the molecular arrangement which was there in the crystalline form no longer exists in the amorphous form. So this is the PXRD of the crystalline celecoxib, which has very characteristic sharp diffraction peaks. So they are indicative of the ordered state of the molecule in a crystal lattice, whereas the PXRD pattern of the amorphous celecoxib is going to be what we call as a halo pattern, HALO. So there is a halo pattern. There are no characteristic peaks in the case of amorphous samples. Similar kind of diffraction pattern would be obtained for all the amorphous APIs if you convert the crystalline form into the amorphous form. We compare in this slide the properties of crystalline and amorphous form. Some of the physicochemical properties are being considered here. So first of all, we'll see the true density differences in the crystalline and the amorphous form. There are three materials that have been taken: indomethacin, sucrose, and lactose. So the true density of crystalline material and the amorphous material is given here, and the percent difference between the true density of crystalline and amorphous is given here. Indomethacin crystalline has a true density of 1.38, whereas amorphous has 1.32. Sucrose has 1.59 for crystalline, 1.43 for amorphous. Lactose has 1.60 for crystalline and 1.48 for the amorphous, which means the true density of the amorphous form is lower than that of the crystalline form in all the cases, and these are the differences in percentage between the crystalline and the amorphous form. Here are some of the other properties. Aqueous solubility is high for the amorphous as compared to the crystalline. Chemical reactivity is also high. Water sorption is also high. Molecular mobility is also high. Physical stability is low. Compressibility would be good. So we have listed some of the properties in green colors, and some of them are there in the red color. The ones that are there in the green color means that they can be exploited in some fruitful manner for the pharmaceutical application, which means the higher aqueous solubility can be exploited for increasing the oral bioavailability, whereas the compressibility could mean that you have a better tabletability. An interplay of the above properties determines the improved functionality, and it also gives the disadvantages to the amorphous system. So the ones that are listed in the red are disadvantageous from a pharmaceutical perspective, because if the chemical reactivity is high, degradation is going to be more. If water sorption is high, then again the physical and the chemical stability are going to be low. When the molecular mobility is high, it will have a tendency to convert back to the crystalline form. So most of the times crystalline and amorphous solids are treated as polymorphs of one another. This is a view which is harmonious with one of the definitions of polymorphism, which says that polymorphism is the phenomena between any solids that share the same liquid state. What it means is, if you melt an amorphous solid and if you melt a crystalline solid, you are going to end up with the same liquid state. Why? Because the molecules that are involved in the formation of the crystalline state or the amorphous form is the same. So if it is salicoxib, after melting you are going to get molten salicoxib. If it is ciprofloxacin, after melting it is going to be molten ciprofloxacin, irrespective of the fact whether you started with the amorphous sample or with the crystalline sample. This is the diagram which shows the formation of the amorphous form. We'll spend some time trying to understand this particular diagram, because this forms the basis of the amorphous form. So on this axis, that is the x-axis, you have the temperature. On this y-axis, you either have the volume or the enthalpy as one of the thermodynamic quantities. Now the starting point is the crystalline state. So this is the crystal, and if you heat the crystal, that is you start increasing the temperature, it will keep on increasing up to this point where the melting point takes place. So depending upon whatever is the melting point of the crystalline form, you will see a step change in the properties, because at this point it will then become a liquid sample. So we are assuming here that during the melting phenomena, no degradation of the sample takes place. So I'll repeat once again. If you take the crystalline sample, you heat it up to its melting point. At that stage, there is a sudden change in the properties of the material as it enters into the liquid molten state. Now, from the liquid molten state, if you suddenly cool the sample, which means you give it a very fast cooling, then instead of crystallizing immediately, it will enter into an equilibrium state, which is called as the supercooled liquid state, which means it will follow this same path and enter into a temperature zone which is lower than its melting point. So in this temperature, it should have actually converted into a solid, but because we did not allow the solidification or crystallization to take place because of the fast cooling, we have entered into a state which is called as the supercooled liquid state. Why we call it supercooled? Because it is at a temperature where it should actually be a solid, but since we did not allow the crystallization to take place, it still remains in a liquid state. It is in equilibration with the line which existed for the liquid sample. Now, if you keep on cooling this further, at some point at a temperature, it will deviate from this equilibrium line. Like for example, it is doing it here and it is also doing it here. And this point of deviation from the equilibrium state is called as the glass transition temperature. So from the supercooled liquid state, now it has entered into the glassy state, which is one type of the amorphous state. Now, why are we showing here glass 1 and glass 2 is because of the fact, depending upon the rate of cooling, this deviation from the equilibrium line can take place at variable temperatures. Sometimes it may take place at a higher temperature, while in other cases you will have to cool further to enter into the glassy state. So, which means that the Tg of the amorphous material is based on the cooling rate that is used for cooling the liquid molten sample. So you can either get glass 1 or glass 1, which means there are multiple glassy states that are possible depending upon the cooling rate that was used. And this glassy state you can see has a higher enthalpy as compared to this glassy state, and during aging or during annealing it will convert back to this stage. Now there are certain other terms which are written out here. So one of the important term that we discussed was the Tg, which is also called as the glass transition temperature. Then there is another term which is shown here called as Tk, which is called as the Cosman temperature. So Cosman temperature is thought to be the lowermost limit of temperature before which the glass transition temperature happens, which means Tk is the lowermost limit for Tg to take place. And how you get the value of Cosman temperature is by extrapolating this equilibrium line and then enter into this dotted line, and the place where it meets the temperature will be called as the Cosman temperature, which means before this Cosman temperature this Tg has to happen. That is what we mean by the lowermost limit of the glass transition temperature. In this slide, we'll discuss the same events that we saw in the last slide in the form of written matter. So a crystalline material at very low temperature shows small increase in enthalpy and volume with respect to temperature, indicative of a certain heat capacity and thermal expansion coefficient. We are talking of temperature which are below its melting point. If you keep on heating the sample at the melting point, that is Tm, there is a discontinuity in both the enthalpy and the volume, representing a first order phase transition to a liquid state, which in layman terms means that the material melts. If you rapidly cool the molten sample, values of enthalpy and volume follow the equilibrium line for the liquid beyond the melting temperature into a supercooled liquid region. This amorphous state has the characteristics of a liquid, but it has a much higher viscosity. This is also called the rubbery state because of its macroscopic properties. What it means is that in the supercooled liquid state, the material will behave like a rubber, which means it will have some kind of flexibility, and it will be able, you can basically consider the normal rubber that you see. So the material will look like a normal rubber. That is why the name rubbery state. If you keep on cooling further, the molecular mobility reduces further to a point where the material is kinetically unable to attain the equilibrium in the time scale of measurement as it loses its thermal energy, resulting in change in temperature dependence of enthalpy and volume. This is basically seen as a deviation in the equilibrium pathway. So I'll go back to the previous slide to show you this aspect more clearly. So we are talking of this equilibrium line continuing up to a point, and thereafter it deviates from this particular equilibrium line. So this is the point where the glass transition temperature is said to take place, or this is called as the TG of the amorphous state. So as it loses its thermal energy, resulting in change and temperature dependence of enthalpy and volume. A change in slope is usually seen at this point, and experimentally it is observed as glass transition temperature, which is abbreviated to TG. At TG, the properties of glassy material deviate from those of the supercooled liquid to a non-equilibrium state, having even a higher enthalpy and volume than the supercooled liquid. We will again go back to the same diagram and see how the glassy material has a H and V value which is higher even than the supercooled liquid state. So you can see this is the glassy state, and the values of enthalpy and volume, say at this temperature, it has a value which is higher than this equilibrium liquid state. That is why we are saying this, and it is also much higher than the crystalline state. So the amorphous sample or the glassy sample has much higher enthalpy and volume at the same temperature as compared to the crystalline solid and as compared to the supercooled liquid state. Below the TG, the material is kinetically frozen into a thermodynamically unstable glassy state with respect to both equilibrium liquid and the crystalline phase, and any further reduction in temperature has very little effect upon its structure. So what we can understand from this discussion is that the overall amorphous state can be broken down into two states. One is called as the supercooled liquid state, which is also the rubbery state, and the other state is called as the glassy state. And why we call it the glassy state? Because in this state the material looks like a normal glass. Glass is the material from which the windows are made. So the glassy material will look like, macroscopically look like a window glass. That is why the name glassy state. Glass transition temperature is the most important characteristic of the amorphous form, because that is the one of the properties that can be experimentally determined for the amorphous form. So as we discussed, amorphous solids can exist in two states, that is the supercooled liquid or the rubbery state. It is a viscous equilibrium liquid form of the material, and the other one is called as the glassy state, a solid non-equilibrium form of the same material. The liquid glass transition or the glass transition is the reversible transition in amorphous material from a hard and relatively brittle glassy state into a molten or rubber-like state called as the supercooled liquid state. Supercooling a viscous liquid into the glass state is called as the vitrification process. If you can recall, there are some materials that are sold in the markets which have this particular terminology attached to them, and the most common one are the bathroom tiles or the tiles that are sold in the market. They are called as the vitrified tiles. What it means is that in that case the material which is used for preparing the tiles has been converted into the amorphous form by a phenomena called as vitrification, and it is done to change the properties of that particular material. TG is the single most important characteristic of the amorphous systems. There is rather a glass transformation range that extends over several Kelvin or more. What we mean by this is that glass transition temperature may not be a sharp point. It will rather happen over a range of temperature. Structural factors affecting TG are molecular size, shape, extent, and strength of the intermolecular interactions. Comparison of the supercooled and the glassy state for a same material. In terms of the physical appearance, it looks like a rubber, whereas a glass looks like a brittle solid. Average time scale of molecular motion is less than 100 seconds in this case, and it is greater than 100 seconds in this case. And there is an asterisk mark which says that the value is picoseconds or nanoseconds in typical liquids. In molecular liquids near TG, it may take minutes or hours for a molecule less than 10 angstrom in diameter to reorient. What we mean by this average time scale of molecular motion is the average time taken by a molecule to move from one place to another in terms of dimensions that are equivalent to the molecular size. This simply also means that in the case of supercooled liquid, the molecules are moving relatively fast as compared to the glassy state, and in the liquid state, the molecules are moving very, very fast because their average time scale of molecular motion is picoseconds or nanoseconds. Viscosity of the supercooled liquid is much higher it will be lower than that of the glassy state because it is a rubber-like state and this is a glass-like state. So the values are 10 to the power minus 3 to 10 to the power 12 Pascal second, whereas for the glassy, it is greater than 10 to the power 12. We'll stop at this particular point and I'll take up the next topic for discussion in the next class. I can understand that this is a new topic which has been started and there could be a few questions related to the understanding of the amorphous state. We'll all clarify those questions with the help of the WhatsApp group that we have created. Before I move over to this next set of slides, which is going to be on the thermodynamic aspects of the glass transition temperature.